So last time I wrote this algorithm, this AKS primality test. In the input, you are given a number n in binary. So first is just this pre-processing. You check whether n is a perfect power or whether n is even, and then if it is, you output composite, of course. If not, then the algorithm, the main part of the algorithm starts. So it finds a number r such that order of n mod r is large, which should be at least 4 log square n plus 1 or more. And then this red check is done. For several a's, you check whether x plus a to the n is x to the n plus a, modulo x to the r minus 1, comma n. If any of these tests fail, then you are sure that n is composite, because it should have passed if n was prime. If all the tests pass for a 1 to 2 square root r log n, then you give up and you say that n is prime. Now we have to show that when we say prime, it is n is indeed prime. Okay, there is no mistake. So for that we identified two groups. The first group is a group of numbers, which is I. So we identified this subgroup I, which is the numbers generated by n. So prime p divides n. So look at this now subgroup generated by n and p mod r. So basically these are product of n power p power, and this group has size at least 4 log square n by assumption. The second subgroup is that of field elements. We are calling it J. So this is the subgroup generated by these polynomials for which the test was done x plus 1 dot dot x plus l, but viewed as field elements. So mod p comma h, where h is an irreducible factor of x to the r minus 1 mod p. This also is a large subgroup. So we showed that J is at least n raised to square root t, 2 square root t in fact. Okay, so now let us use these two lower bounds, these two big subgroups, to get what we want, the correctness proof of the algorithm. So note that J is a cyclic subgroup of the field. Why is that? Well, because this multiplicative subgroup of the finite field is cyclic. So every subgroup is cyclic. J in particular is also cyclic. So the way you can use it is, since the size of I, the subgroup I, is T, there exist two different pairs between all smaller than square root t, at most square root t, such that n raised to I p raised to j is n raised to I prime p raised to j prime mod r. Right, this is true because the number of n raised to I p raised to j is more than square root t times square root t. which is more than t, but the size of the subgroup I is only t, which means that two elements will be the same. So we can find ij and I prime j prime such that they are the same mod R. But ij and I prime j prime are different pairs. Now for these two pairs, what can you deduce? So let F be a generator of J. J is a cyclic subgroup, pick a generator, call it F. Then you know that f of x to the n to the I p raised to j is the same as f of x to the n to the I prime p to the j prime in the finite field, right? Simply because this n to the I p raised to j and n raised to I prime p raised to j prime, they are the same mod R. So these x powers are the same, so f evaluations are the same. But then by step 4 of the algorithm, what is step 4 of the algorithm? Step 4 is this red test. The red test is passing. So if x plus a to the n is x to the n plus a, then since f is a product of such things, you get that LHS will be equal to f raised to n raised to I p raised to j, and RHS will be equal to f raised to n raised to I prime p raised to j prime mod p comma h. But f is an element of high order, right? So this means that in fact size of j should divide n raised to I p raised to j minus p raised to j prime. Right, so this is a very important step. This is the key step which will finish the proof because we are deducing from the fact that these two products are same mod R. We are deducing that in fact they are the same modulo a much bigger number, which is size of j. So what does that mean? So since n raised to I p raised to j and n raised to I prime p raised to j prime, both of them in value is smaller than n raised to 2 root t, which is smaller than the size of j, what you deduce is that they are absolutely equal, not just mod, absolute equality, which means that n is a power of p. But n cannot be a perfect power, that we have ruled out in pre-processing step 1. So that gives you the contradiction. Okay, so this means that if step 4 passes, then n has to be prime. Okay, that finishes the proof. So this algorithm, steps 1 to 4, this algorithm takes remember log to the 10.5n time This is the time complexity, and if n is composite, it outputs composite. If n is prime, it outputs prime. Right. So that's the full proof of AK's primality test. So you have seen some very practical primality test. You have seen this deterministic polynomial time primality test. Next question is, once you have verified that n is composite, how do you find factors? Integer factoring. Let's start with that. So this area of integer factoring consists of only heuristics. Okay, the formal algorithms and formal analysis is currently missing. Even at the level of heuristics, these algorithms are not fast. But whatever there is, we'll study so that it gives you an idea of how possibly you can factor integers that are not too large. So the general algorithms to factor n are slow, in fact very slow. Okay, so currently only integers in around 700 bits, which in terms of decimal digits is 200 digits. So around integers of around 200 digits, okay, up to that could be factored. That too using specialized hardware. Okay, so 200 digit long integers are still quite large. They are like 10 raised to 200 in value. It's amazing that they can be factored in practice, but anything bigger than that, it's very hard to get to an answer. Okay, even for specialized hardware, this is a very tough problem. It takes forever to find a prime factor or any factor. Theoretically, the situation is quite bad. So the best provable complexity that is known is expected time. So all these are randomized algorithms, heuristics. Expected time is 2 raised to big O of log n times log n square root. Okay, so compare this with brute force. Brute force is exponential in log n, and here you have square root of that in the exponent. So it is certainly faster, but it is still not polynomial time, and it is not very practical if log n is large. And heuristic complexity is slightly better. It is 1/3 here and 2/3 here. Okay, So heuristic is kind of 1/3 of log n, log n to the 1/3. Provable is log n to the half, and this is happening in the exponent. So this is a weird complexity function, right? We haven't seen this before. Let us talk about it a bit. We'll use the notation Lx alpha comma c to denote this exponential in c times log to the alpha x log to the 1 minus alpha log x. And to be sure, this log is natural log. That's important because we want to really talk about the constant multiples as well here, because that may change the practice of it, how fast it will be in practice. So we want c to be small, and also we also want this log to the alpha x to be small, log x to the alpha to be small. So the best algorithm known is due to an analysis by Pomerance. It's called the general number field sieve. In short, GNFS. Number field sieve is NFS, generalized number field sieve is GNFS. So using a GNFS, you can factor integers in the fastest possible way currently. It has conjectured time complexity. ln 1/3 2. Okay, so exponential in 2 times log x to the log n to the 1/3 times log x log n to the 2/3. Okay, the dominating part is log to the 1/3. That is the conjectured complexity of GNFS. So in these 2 lectures, last remaining lectures, you will get a good idea of how this is done. Okay, you will not be able to see all the details, but you will get the basic idea. So let us start with the reason why this function appears. And the reason for this is actually quite interesting and a very important topic. It's the topic of smooth numbers. Smooth numbers are basically numbers that have small prime factors. So number n is called y smooth if all its prime factors are less than equal to y. Okay, then we call okay, let me call it m. So number m is called y smooth if all the prime factors of m, every prime factor is smaller than less than equal to y. Their density will be important. How many numbers below x are y smooth? So their density is denoted by psi x comma y, and this is the number of m such that m is y smooth. Okay, so psi x comma y divided by x, you can say, is the density. Okay, so we are interested in this as a function of x and y. So it is actually this density that decides the complexity of integer factoring algorithms. So asymptotic estimates for psi x comma y determine the complexity of advanced integer factoring algorithms. So let us first see a proof sketch of a good estimate of psi. So this was shown by Dickman, De Bruyn, it's an old result. So it says that psi x comma y is at least x divided by u to the u, where u is log of x base y, which is also the same as log x by log y. Okay, so in terms of this ratio of log x log y, the density of y smooth numbers up to x is u raised to minus u. So let us see a proof sketch. It will not give the full result, but it will give a decent estimate, and you will see why u to the u and then why this L function appears. Consider the regime. So let's take u to be at least log y. Okay, so u is not very small, and we also don't want u to be very large in the proof. So our proof will work when u is not very small and it is not very large. So for example, this in particular means that y has to be large as well. Y cannot be too small, because u less than y over log y means that y has to be more than log x. Okay, so if y is smaller than log x, then the proof will not work. And similarly, y should not be too large, because this first inequality means that log y should be less than, or log y whole square should be less than log x. So y should not be too large. Okay, so under this, in this regime, the proof works. What is the proof? Actually, now the proof is very simple. The proof idea is very simple. It is that you consider the primes that are less than or equal to y. So consider all the primes that are y or less. We'll call them P1 to Pt. Notice that the prime numbers are, they are asymptotically, they are like y over log y. So they are around t many. So let's enumerate them, P1 to Pt. And now these are, this is kind of the base on which you will build smooth numbers, m. Right, so you will multiply these primes with repetition. So any y smooth number m will look like product of pi to the alpha I. So this means that the number of numbers, such numbers you will get below x, if you take alpha i's, appropriate alpha i's, then this product will be below x, right? So in particular, you can use these alpha i's such that the sum of alpha I is less than or equal to u. Because u is log x by log of x to base y. Pi's are all smaller than y, right? So if the sum of alpha I is less than or equal to u, then this product of pi alpha I is smaller than x. That was the reason we defined u actually like that. And this then is, at least you use the binomial estimate. So u plus t, choose t. Then you use this simple estimate of t by u to the u. T is, in our regime, t is bigger than u. So u plus t, choose t will be t by u raised to u. And then you substitute for t. So you get y raised to u divided by u times log y to the u, which is, what is y to the u? Y to the u is x. What is u times log y? That is log x. Okay, so that is some decent estimate. It's still not like u to the u, because u is actually smaller than log x, but we can stop here because x by log x to the u is giving us some idea of how many y smooth numbers there are below x. But this can be made more refined, and then you can get this de Bruyn's estimate. So let us assume that it will work. So then using that theorem or estimate, first thing you can observe is this bound is non-trivial only if u raised to u is sufficiently smaller than x. Otherwise, x over u raised to u will become 1 or less. That won't make much sense. But if u raised to u is much smaller, then x over u raised to u is a decent quantity, so that's a good lower bound. And for that to happen, y should not be too small. If y is too small, like a constant, then your u is log x, and then u raised to u will be much more than x. So y shouldn't be too small, it shouldn't be too large, right? That was our regime anyways in the proof. So let us clearly write down u as a function of x and y, which will work, and then you will see the L function. So a useful tolerable y is Lx alpha comma c for constants alpha c. So x is the variable. If you take alpha c to be absolute constants, then for this y equal to Lx alpha comma c, this de Bruyn estimate will be good. So in that case, u raised to u comes out to be actually Lx 1 minus alpha by c. So u raised to u one minus alpha appears there in the second exponent if you started with alpha. Okay, let us look at the calculation, because this is an important way to understand the reason why this strange function appears. So what is log y? Log y is log of this Lx alpha comma c, which by definition, if you look at the definition, it will be what? We ignore the constants and we come to the main function, which is log x to the alpha times log 1 minus alpha log x. This is what log y is. So what is u? So this will be, you just want to divide by the above quantity, right? Log x divided by that. So you will get, let me make this exact because I need that. This actually is just c times its base. It was exponent, exp function was base e. So this is just c times log alpha times log 1 minus alpha log. So then I can write it exactly. So this is equal to 1 over c times log of 1 minus alpha and log of alpha minus 1 log x. Right, that's what you get. What is u raised to u? Let's calculate u raised to u. So which is instead, to keep calculation manageable, we'll work with u times log u. So u times log u will be the above. So 1 by c times log of this times log of alpha minus 1 log x, and log of u will be, okay, so here I make some approximation. So I forget about log of 1 by c because it's only a constant contribution. Log to the 1 minus alpha gives me 1 minus alpha log x. And I get some again additive lower order term log of x, which I ignore. So let's just make it approximate instead of doing the exact calculation. And then you will notice that this is coming out to be 1 minus alpha by c times one minus alpha in the exponent, and then you have log of x to the alpha. So which means that u raised to u will be e of this, e raised to this, right, which is same as Lx 1 minus alpha comma 1 minus alpha by c. That's the full calculation. Okay, so you get that u raised to u is again L of 1 minus alpha if u was L of alpha. So that's a nice relationship. It will keep appearing in integer factoring analysis. So let us collect this, make it a theorem. So if you take y to be Lx alpha c, then the probability of choosing a y smooth m less than equal to x, this probability is psi x comma y, the number of y smooth numbers divided by x, and it is 1 over the previous bound that we got. So Lx 1 minus alpha, so alpha minus 1 by c. Okay, this is really the probability of y smooth numbers when y you take as an L function, L of constants. So for L of constants, such smooth numbers is actually decent. It's again L of constant. So that's the reason why L function appears. So in integer factoring algorithms, the time spent it depends on the bound y and the probability because 1 over probability is expectation. So you have to try these many numbers to get a smooth number. Okay, so actually the time complexity of integer factoring uses this L function. Another point is time complexity of this form ln alpha comma c, where alpha is of course less than 1. This is termed in the literature of integer factoring, this is termed sub-exponential. Why is it termed sub-exponential? Sub-exponential time complexity? To contrast with ln 1 comma c. What is ln 1 comma c? ln 1 comma c is exponential in c times log x, right, which is x to the n. So n to the c for any constant c, no matter how small the constant c is, this is a very slow algorithm because n will be huge in value. That is clearly exponential time, and if you can reduce alpha below 1, then in the literature it is called sub-exponential. So for example, Eratosthenes sieve So Eratosthenes sieve is just you divide by all numbers from 2 to square root n to factor n, right. So the complexity will be around square root n, which is a half c equal to half. So that takes ln 1 comma half time. Okay, so we are up against that. ln 1 comma half is kind of the trivial algorithm to factor n. That we want to reduce to ln alpha comma c, where alpha is less than 1. Okay, so much for the L function and smooth numbers. Now let us look at some concrete factoring algorithms. We'll start with an easy one, but they are still better than Eratosthenes sieve, better than the brute force. So let's start with some special case factoring algorithms. So they will they work better than brute force on special numbers n. They make some assumption on n, then they work better. So first is, it's called Pollard's row method. What does it do? So suppose one of the prime factors p of n is moderately small. You want to use that fact. Obviously, if you enumerate numbers from 1 to p, then it will take step p. But can you do better than p? That is what Pollard's row method does. So idea is to exploit the presence of a moderately small p dividing n. Say you want to solve it in square root p time instead of trivial p. So brute force would have been O tilde p, right? You want to do better than that. So this is a clever algorithm. It will achieve square root p. How it will do it is it will take a random looking function f and it will start with a value with a point x, and then it will apply f on x again and again. Application of f on x again and again. So let us first write down the algorithm. Input is odd n and a pseudo random function f actually you can even take f to be x square plus 1 mod n. Just introduce some non-linearity, and then usually these non-linear functions, they behave in a pseudo-random way. So factor n in O tilde square root p times log n time. That's the goal, factoring in square root p time. Let's write down the algorithm. The algorithm, as I said, randomly picks a starting point. And let's take another variable y, set it equal to x, and let's set a new variable, third variable d to be 1. Then what you do, there is a kind of an infinite while loop. What it does is compute apply f on x and apply f on fy. So on x you apply f once, on y you apply f twice. And then you compute the GCD of x minus y with n, basically checking whether x is y mod n. You are taking the difference, or think in terms of prime p dividing n. So you are trying to check whether x and y are the same mod p. If they are, then d will become p heuristically. So if that happens, so if d is not equal to n, then output D. So this loop will come out only when D is not 1, right. So D is between 1 and n. If it is not 1, it may also be n, but if it is neither 1 nor n, then it's a prime factor, then it's a factor of n. So that's a success case, otherwise you will say fail. And then probably you have to repeat the experiment. Okay, that's the algorithm. So we'll make two assumptions and then analyze this. So assumption is P is the smallest prime factor of n, and second is that if you keep applying f on x, then you get a random sequence. Okay, so let's say P is the smallest factor of n, so it's prime, and if you keep applying f on x, then you get a random sequence with these two reasonable assumptions. In fact, the assumption is only the second one. With that assumption, we'll show that it takes square root p time. Okay, so with these two assumptions, what we will show is that with high probability in step 2, P will divide x minus y within square root P iterations. Okay, that's what we claim. So this while loop in step 2 will not really be infinite. Very soon, which is square root p iterations, it's highly non-trivial because we are just applying f once and f twice again and again on x and y respectively. But within square root p iterations, it is expected that this difference will be divisible by p, and so we'll come out and output a factor of n. Obviously, this is a heuristic. Using the assumption, it's a probabilistic claim. So how do you show this? Well, since you are assuming that this f applied I times on x is a random sequence, so the probability of f 0 I x viewed mod p for, let's say, I 0 to j minus 1. So these being distinct, there is an upper bound on this probability, right, because the numbers, the residues you can get is 0, 1, 2 dot dot p minus 1. So in the first case, for I equal to 0, this can be any value. So that probability is basically 1. So I write it as p over p possibilities. In the second case, since you don't want to overlap with the first one, this is p minus 1 by p. And in the end, you get p minus j plus 1 by p, which I write as you go up to maybe you go up to j. So at I equal to j, you have this p minus j excluded. So it's p minus j by p. So you see this as 1 minus 1 over p dot 1 minus j over p. So this is e raised to minus 1 over p minus 2 over p dot dot minus j over p, which is around e raised to minus j square by p. That's the probability estimate. So if you take j to be less than square root p by 2 or square root p by 10, then you see that this probability is sufficiently small. So these elements in the sequence, random sequence, being different mod p is actually low probability. So with high probability there is an overlap. And overlap means that the difference will be divisible by p. So this implies that for j smaller than square root p, the probability for a suitable fixing of j, let's say square root p by 10, the probability of a repetition obviously mod p is good. This calculation should remind you of something called the Birdet paradox. Okay, that's what is going on here. So if you collect square root p random things, then numbers, then 2 of them will be the same mod p. That is what it is saying. So this means that there exists I1, I2 at most square root p such that f applied I1 times is the same as f applied I2 times mod p. So this seems, so how does this relate to step 2 of the algorithm? Right, there we were just applying x, we were applying f once, and y we were applying it twice. So how does this relate to what we have deduced in terms of I1, I2? So we are almost there, we just have to connect it properly. So after the, what is happening is that you started with something and then in the sequence f composed I times x mod p, that starts with some value and then it starts repeating. Okay, so this is the 0th iteration, this is the I1th iteration, and then let's say this period is r. So so this will be the I1 plus tth iteration, and this will be I1 plus r minus 1th iteration, and in the next iteration, which is I1 plus r, the thing repeats. Okay, so this is how it is moving forward. Okay, so this is also the reason why it's called the row method, because you can look at this picture how the iterations are going, which is how the sequence f I x mod p is changing. So it may start at some value, but after few iterations, that particular value after at the I1th iteration, that particular value will repeat with period r. So let r defined to be I2 minus I1 be the period. That is what we have learnt. This happens with high probability, this row picture. So in step 2, what happens? So I1 plus tth iteration of step 2 gives us I1 plus tth times composed x with f and twice that on x. Right, these are the two values you are getting, because x you are going one step at a time, y you are going 2 steps. So in I1 plus tth iteration you are getting I1 plus t and 2 times I1 plus t. So a collision occurs, that's the key thing. So collision mod p happens if these two values overlap mod r, the period. That's the period of the circle in row, which means that the first time you will see the collision, right, that will be when t is equal to r minus I1. This is the first collision. So I1 plus t, you take it to be r, and at that iteration you will see the collision, and hence we are done. So this means that p will divide x minus y at r, which is at most square root p iteration of step 2. Okay, so this finishes the proof of this lemma statement in blue. With high probability p will divide x minus y in step 2 in only square root p iterations. So the time complexity of this is, so with high probability p divides d in step 2 in O tilde square root p iterations, and in each iteration you are doing everything in around log n time. So that's the algorithm, Pollard's row algorithm. Okay.